to tell you about some of the work that my team has been doing, and I'd just like to thank the organizers for the opportunity to show you this. So I'll be talking about how we can look in astrochemical environments to try to see some of the basic building blocks of life and see how complex they get as planets start to form. And we can use the James Webb Space Telescope for this. So as an outline for the talk, I'd like to explain a little bit about why ice chemistry is really important for understanding astrobiology. You may not immediately connect, warm living environments on Earth with the cold regions of space that I'm going to be talking about. Then I'd like to also explain why JWST is the essential instrument for studying these ices. And this is a preview of the results that I'll talk about. I'll show this slide at the end again, but I'll talk a little bit about setting the elemental budget for planets that will eventually form life, as well as how mixed ices are actually really important for understanding how planets get this elemental budget, and then talking about complex ice environments and the implications of these for planet formation. So to start off, we know that life has several basic building blocks. The four most abundant of which are carbon, hydrogen, oxygen, and nitrogen. And we will typically refer to these as CHONs, which is a jargon acronym throughout the rest of the talk. And even though these are really common in human bodies, actually they're really confined only to this very thin skin on the surface of Earth. The rest of Earth is mostly rocky elements like iron or magnesium or silicon. And we think that these CHONS elements were actually brought to Earth by collisions with small bodies in our solar system. Could have been comets like this comet 67P from the Rosetta mission a few years ago, or it could have been asteroids that might have a little bit of ice mixed in with them. And these elements were carried primarily by things like simple ices like water, carbon monoxide, carbon dioxide, methane, and ammonia, or more complex organic molecules like methanol, acetaldehyde, and dimethyl ether. Now, what do I mean by a complex molecule versus a simple molecule? So carbon monoxide is an example of a simple molecule. It just has two atoms in it. Whereas once you start to get more than six atoms, including one containing carbon, like methanol, this example here in the middle, then you become a complex organic molecule. And these complex organic molecules can react together to form biomolecules eventually. So this is an example of a biomolecule glycine, which is the simplest amino acid. And we would really like to understand in the context of habitability and astrobiology, how in what format do planets receive these CHONS elements? Do they receive them mostly as simple molecules, or maybe do they get some of these complex organic molecules with them? Because that could actually maybe accelerate the formation of life a little bit. Now, the ices that end up in comets, which carry these molecules, actually form initially in these cold regions of the interstellar medium, which is the space in between stars. So they form where you have a molecular cloud that's very dense and very cold and shielded from starlight. And there's these regions of molecular clouds. This is a famous example that was taken with the Hubble Space Telescope. If you imagine you can zoom in certain regions here, and they'll be very, very dense and very cold. And in these regions, we call them prestellar cores, you can start to collapse material toward the center of the core to form a central star, and that starts your T equals 0 for star formation. That central star will then be surrounded by a protoplanetary disk that spirals material from the outer edge in toward the central star, and that disk will be fed by a protostellar envelope that connects the disk with the remaining molecular cloud material. After about 1 million years, that envelope surrounding this disk dissipates, and you're left with just the protoplanetary disk component. And we see in these systems, we can already start to see, in some cases, gas giant planets that are forming in gaps in these disks around 1 to 10 million years old. So we know that we can see planet formation that's happening right there. Eventually, after about 10 million years, this disk will dissipate, leaving all of the planets, comets, and asteroids left over. And then we'll eventually, in several billions of years, get something like our solar system, which is about 4.5 billion years old. And that will include both, planets and these cometary bodies. So, how do why is it important? Oh, I'm gonna go back here once more. One thing that I forgot to point out here is that at each stage in the process, there's something that changes aside from the physical structure. You also have a change in the temperature. So these prestellar cores are very cold, and then that material heats up as you approach the central star, because generally close to the star it's warmer, and further from the star it's colder. And then in the disk itself, you also have a temperature gradient. So if we're looking at the ices that form in these molecular clouds, they start to assume a sort of gumball-like structure. So in this gumball, you have a center which contains the gum, and then layers of different flavored candies on top of it. And if we think about these grains from the molecular cloud, um, they have a silicate core, and this silicate core is like something that formed in winds around massive stars somewhere else in the galaxy, and then these silicates condensed out of that and then made their way into these molecular clouds. And then on top of this silicate core, you have some refractory carbon, and then additionally layers of different ices, moving from ices that sublimate at high temperatures, like water ice, to ices that sublimate at low temperatures, like carbon monoxide ice. So you have this very layered structure in the grain. And the impact of this structure, if you look at, say, the protoplanetary disk stage, as I said a couple slides ago, you have in the disk a much warmer environment close to the star because the star is really hot, and it gets colder as you get further away in the disk. And this means that as you have these icy grains that enter the disk from this protostellar envelope, and they start moving, spiraling in toward the star, they sublimate layers of ices off of their surface in a predictable pattern according to the temperature of the particular ice species. So first you sublimate, things that are very volatile, like this carbon monoxide ice, and then eventually you'll even sublimate water ice, and then at some point you actually sublimate all of the carbon layer as well, and very close to the star you vaporize all of your grain, including the rocky silicate core. And this is important because planets that form at different points in this disk will have access to a different set of solid materials depending on where they formed in that disk. Because out here they'll have access to ice, and here they'll only have access to more refractory materials. And this gives rise to this sort of map of these disks where, as you have different snow lines, you remove material from the solid phase and put it into the gas phase. So a lot of people who study exoplanets will characterize atmospheres by whether they have like what sort of carbon to oxygen ratio they have in their atmospheres. So essentially you can get different types of planets that form in different parts of the disks based on what we think this map looks like. So if we want to answer questions like, do other terrestrial planets like Earth get sufficient amounts of carbon and also like water-rich solids in order for them to become habitable someday and for life to arise on these planets, we need to study the ice abundances all the way in molecular clouds and trace those ice abundances as they change throughout the protostellar envelope and into disks to understand how much material from these basic Chance elements each planet can inherit. So that's the overall goal for what I'll be talking about today. Um, how we do this is we look in the infrared. So this is an example of a spectrum for water in the infrared between 2.5 microns and 20 microns. So water has different ways of moving. This is an example of 6 different ways that the water can move. It can stretch, it can rotate, it can bend back and forth. And each of those different modes, I'm going to stop this now before I get dizzy. Each of those different modes uh, has a particular frequency for the motion. And those frequencies will correspond to a particular wavelength in the infrared typically. And that's where you'll get features like this. So water has this spectral feature here around 3 microns that corresponds to an OH stretch in the I think this first stretch here. And then there are additional features further away. And each ice species has sort of a characteristic fingerprint that you can get from these different features. So you can see that carbon monoxide, which doesn't have a hydrogen in it, doesn't have the OH stretch. Instead, it has a CO stretch at around 4.7 microns here. Um, and if we look at different more complex molecules, like say methanol, which is the simplest complex organic molecule that we talked about earlier, it also has an OH stretch, but then it has a large number of small features that have these different wavelengths. And again, these act like a characteristic fingerprint. If you look at all the small features, you can try to estimate um, what different types of molecules you have. So you can see that for methanol, it has this CH stretch mode here, right next to the OH stretch mode. And almost all of the complex organic molecules will have this because they all have carbon and hydrogen. But again, if you look at, in particular, the weaker features around 6 to 10 microns and take ratios between those, then you can identify what type of comms you have. So that's what we'd like to do, but then we have to be able to observe these wavelengths, and that's a little complicated. And this is because this is a plot that shows you different materials, so silicates in orange, graphite in black, and water ice in blue, and they're plotted against wavelength. And on the bottom part of the plot, you can see the regions of this wavelength space where Earth's atmosphere absorbs a lot of radiation from space. So basically, you can see that there's a this is atmospheric absorption. So in the visible wavelength range, where we put this rainbow, we can see things in visible light on Earth because there's a opacity gap in the Earth's atmosphere, so that lets the light through. But a lot of the wavelength regions where we have these key ice features are actually places where Earth's atmosphere absorbs a lot of radiation, in part because Earth's atmosphere has all of these ices in it, right? So we need to find a way to get beyond Earth's atmosphere so we can see these ices. So we have to go to space. And this is an example of a protostellar spectrum. The first part was taken from the ground, so you can see that you're capturing some of these key ice species, but there's also some critical gaps, like if you wanted to see CO2, for example. And if we go to space, which is the longer wavelength part of the spectrum, you can start to see a whole bunch of these different ice and silicate features. So the good news is we just got the James Webb Space Telescope launched in 2021. It can observe from 0.9 to 28 microns, which covers all of the essential wavelengths for these ices that we're interested in. It's 50 times more sensitive than the previous space mission, which is the one that produced this mid-infrared spectrum here. And it has also 25 times more spectral resolution than that mission. So you can see very narrow lines like that CO stretch that we pointed out in carbon monoxide on a previous slide. So one of the first programs that we had with JWST to observe ices was the Ice Age Early Release Science Program, which is the program that I'm the PI for. And In this program, we looked at a particular molecular cloud in the chameleon-1 star forming region. And the molecular cloud material here is indicated in red. And you can see that there are a number of different green and blue targets in here. Um, and I've indicated with crosses some specific sources that we targeted with this program. So there's a prestellar core and a class 0 protostar, which is one of the earliest stages of protostars. And those are both probed by observations of background stars that have lines of sight that pierce through the envelopes around these sources. And then there was a class 1 protostar and a class 2 edge-on protoplanetary disk. So we can trace ices in each of these to try to see how the ice evolves as a function of the star formation sequence that I showed earlier. So I'm going to show you next a zoom in on this particular region with the NearCam instrument on JWST. And you can see how much more spectacular that is. You have really, really, really fine details. Suddenly, instead of just seeing blobs, you're actually seeing structure in these protostars, and you can see diffraction spikes coming from a number of these other protostars. Some of them are resolved into two separate stars. You can also see a number of very faint galaxies here, here, and here, and here in this picture. Um, and I'm going to focus for the rest of the talk. It's a beautiful picture. I encourage you to go in and look at it at high resolution. But I'll focus the talk on the two background stars here that I've circled, where we can see the ices that are in this cloud. So this is the spectrum that we got for the brightest of those background stars, and it just is spectacular. It's full of all sorts of the features that we're interested in. Here's that OH stretch for water and the CO stretch for carbon monoxide. Um, and the just it's full of ices. And then if I zoom in on so those are the major ice species right there that are most important for carrying the Chans elements. If we zoom in on the weakest features, that's actually where a lot of the new science is. So we see that there's some structure in the carbon dioxide ice band, which is something that can indicate the shape of the grain that it's on. We also see isotopes, so heavy versions of the different molecules, so heavy carbon dioxide versus normal carbon dioxide, heavy CO versus normal CO. But there's a couple of key points here. We also detect for the first time OCS, which is a molecule that has sulfur in it in a molecular cloud. It hadn't been previously detected in molecular clouds before. And we also detect SO2 in this wing of this feature. So now we're able to actually constrain something about the sulfur budget. So sulfur was another one of these volatile elements that we're interested in. And we're getting for the first time a complete set of all of the different carbon-bearing species for the ices. So that's really, really important. And if we put all this together, we're able to model all of those spectra. And the model looks very close to the spectrum, so I won't bother showing it. But with that, we're able to get the amounts of ices relative to water. And we can add everything up and see that we know what sort of amounts of each element we would expect in this molecular cloud because we know what the cosmic abundances of each of these elements are. So we can say that we're actually able to see with the ices about 50% of the carbon and about 31% of the oxygen budget. And about 13% of the nitrogen budget, and only 2%, we were able to detect sulfur for the first time, but it's only 2% of the total expected sulfur budget. So this is suggesting that refractory solids are actually really important for all four of these elements. So I'll focus on ices for the rest of the talk, but it's worth noting that for planetary compositions, refractories will play an important role. So just to emphasize again the connection between the elements that we see here and the atmospheres of planets outside of our solar system, this is another JWST result from one of the exoplanet teams, and you can see they're detecting all of these ices, or they're detecting gas phase molecules that are the same molecules that we detect in the ices. So we have SO2, carbon dioxide, carbon monoxide, and water. So it's really there's a really critical connection between the icy grains that we see in these cold regions and exoplanets. Now, even though we saw that there needed to be about 50% refractory carbon in order to match the carbon budget that we have, we don't actually see any refractory carbon features in the spectrum. So we looked for what's called polycyclic aromatic hydrocarbons, which is a fancy way of saying either rings of different carbon and hydrogen atoms or long strands of these atoms. But the features were not there, so they're probably hidden somewhere. And we'll come back to this a little bit later in the talk. One other thing that we were able to identify from these spectra is that we thought prior to JWST that we had that there was one primary way that we might say form the complex organic molecules, and that was that you would have your bare silicate grain. You would form, like I said earlier, these progressive layers of ices, starting with water, and then building your way up to then a layer that contains carbon monoxide as well as carbon dioxide. And this is because water forms directly on the grain surface, and carbon monoxide actually freezes out onto the grain from the gas phase. And then we thought at that point there were chemical reactions that would occur on the surface of the grain once you had formed carbon monoxide on the surface, that would then form methanol, the simplest complex organic molecule. And in looking at our observations, we can actually fit each of these features with different with different blends of ices. So we can fit this with a pure carbon monoxide component, and then a component that's carbon monoxide mixed with carbon dioxide, and a component that's carbon monoxide mixed with methanol. So we can definitely see this stage, which is what we expected. But if we look at other features, so this is right here around 9.5 microns, this is a methanol feature. We can see that there's a methanol mixed with CO component here in purple, but there's also a methanol mixed with water component. And this was something that we hadn't necessarily expected, but it turns out that when we talked with our colleagues who are on the team who are astrochemists and they do chemical modeling, they were actually able to point us to several laboratory studies and their own chemical models that predicted that you could potentially form complex organic molecules really early. Additionally, we also see that we have in the CO2 feature, we have a CO2 component that's mixed with water. So there's mixed ices in the water-rich phase, including complex organic molecules. So these are forming much earlier than we had anticipated. And this is really cool because it could mean that maybe you have these complex organic molecules in the ices in the cloud, and then you could disperse them into every star system, and that could potentially be something that helps to again kickstart life a little bit. So we saw this feature of methanol, and that it looked like it formed with water and formed early. So what about the other weaker features for complex organic molecules that I had mentioned on one of the earlier slides? Well, we can look in this region of the spectrum here, which is the sort of 6 to 8 micron region that we'd mentioned earlier, and blow it up. And the quality of this data is so good. This is a signal to noise on the continuum of about 400. So even though it looks like these are really faint wiggles, When we fit a polynomial here and we can blow it up really big, these are the error bars here, and you can see that really these features are actually really quite real. So we matched some laboratory data to these features, and it looks like we have both ethanol, which is the kind of alcohol that you might drink, and acetaldehyde, which is this feature here in blue. And there have been a couple other um, JWST programs that have had targeted these lines before, or these features before in protostars. So this is another a protostar fit here. But then since then, there's been another program, the JOICE Plus program, which has some overlap with the Ice Age team. And they've done a really detailed job of starting to fit these features in other protostars. So they were able to fit all of these different types of ices to this set of features. And again, you see they have ethanol in here as well. And I think this was something that was in a big press release when it came out. Cheers to JWST because they had alcohol in it. So all of these features are very clearly here. And so we're starting to see in this case, a lot of them are also mixed with water. If you look down here, they're in a blend with water. So it looks like they must have formed early. And as we saw from our own Ice Age work, it looks like they already formed in the molecular cloud. Now, we can use other evidence that we see in our molecular cloud ices to confirm that that the ice mixtures are really important in the cloud. So we can look at this weak feature that I briefly flashed on the screen earlier. This is the main water OH stretch feature here at 3 microns. But in the blue, the shorter wavelength wing of the feature, there's this little itty bitty tiny feature, these two features here. And these are called dangling OH. And they occur when you have an ice and either the ice has a pore in it, so you have one OH, the oxygen and the hydrogen are connected to the rest of the ice, but there's a hydrogen that's just sort of dangling off into the ether. Or it could be a situation where you have one of the hydrogens is again connected into the water ice matrix, but the other hydrogen has bonded with some other molecule in the mixture. So it could either be from porous ices or mixed ices. And we see these in a large number, 8 of the molecular cloud spectra, and it's very clearly here. So we think it's likely that this is a signature of mixed ices that we saw in the profile fits earlier. Now, the fact that we see these mixed ices could be important because as I said when I was showing you that sequence for star formation, the ices start out cold, but then they fall in through this protostellar envelope toward the protostar and they start to warm up. And when they start to warm up, the more volatile ice species that sublimate at lower temperatures start to come off of the surface into the gas phase. So, like CO, for example, should in this model vaporize first, leaving the other layers intact. So if you have a mixed ice, then this could be a way to essentially trap some of that more volatile material on the surface of the grain and preserve it from the molecular cloud into the comet forming region of protoplanetary disks. So this is something that we're interested to see whether or not we see evidence for the different ices coming off of the grains. So there have been some other studies from the IPA JWST team where they looked at this 13 CO2, so that the heavy CO2 feature, which is indicated here in this, all of these plots are of that same feature. But in this particular case, 3 protostars in this program show a feature that's clearly CO2 mixed with water. But then once you once you start to look at the whole set, there are two protostars which have some kind of heating or outburst going on where the star is getting brighter. And it looks like in this case, you're actually able to see a component that looks like it's pure CO2, so not the mixed with water component. The water component is still there on the red side, but this blue component shows up, which appears to be pure CO2. So it's clear that in that first in the protostars themselves in the envelopes, um, that the CO2 water mix is really strong, and it's important to keep that in mind for understanding the carbon budget that makes it into the disk, because normally CO2 would vaporize. But in some cases, we are seeing that that CO2 is actually vaporizing. So it's still a bit of an open question. When you get to the disk stage, how much of that CO2 has come off of the ice grain and how much is still left in it? Um, so we looked at in going back to the Ice Age program, we did have this disk in our program, and the reason that it's important that this disk is an edge-on disk because when it's edge-on, we can actually see some of the ice features in absorption, like these features, against um, the continuum in the mid-infrared. Um, and we know that this is the geometry that we have for this disk because we observed it using the MIRI MRS mode and the near spec IFU mode of JWST. And these two modes essentially take a picture with a coarse number of pixels at each wavelength. So you can actually see the spatial structure of the target that you're looking at. And in this particular case, this inset shows the spatial structure. So we have the edge on disk looks a bit like a hamburger where we have a bright red bun. The dark lane is the burger, and then there's a green bun at the bottom as well. And they have jets that are going perpendicular to the burger in the system. So we can see all of these ices. And interestingly, I'll get to it in a moment, we also see some refractory carbon features. But we see the ices, and we're able to get the first complete ice inventory for a protoplanetary disk. Um, and if we look over here, we can uh, zoom in on just the part of the spectrum that contains most of the ices. So the near infrared part from like 3 to 5 microns. And um, once you remove the continuum to calculate how deep these ice features are, you can then take an individual feature and essentially, because it's this image at every wavelength, you can create a map of the spatial distribution for those ices. So this here is the water ice map that we get from this water ice feature. So the bright yellow indicates where there's more ice, and the sort of magenta color indicates where there's less ice. And if we sort of slice this map up into different cuts, then we can get sort of a profile for how much the ice content changes as you go from the bottom of the disk to the top of the disk. So this is in the middle panel what that profile looks like. You can see that basically the largest amount of ice where the most ice is right here is corresponds to the midplane of the disk, sort of where you would expect the burger to be if it's a hamburger. And then you do have a decreasing amount of ice, so it's decreasing in this direction as you move into the upper layers of the disk. However, what we actually expected to see was something much more pronounced, where you have a lot of ice in the midplane and then very little ice in the upper layers. And we expected that there would be differences between how much CO ice we had in the upper layer versus CO2 ice versus water ice. So this was sort of what we expected to see here on the right. And it doesn't match what we actually saw. So based on what we actually saw, we think that what we're seeing is that CO ice, which you would expect to sublimate at lower temperatures than, say, water ice, that the CO ice is actually trapped inside of a mixture with the CO2 ice or with the water ice. And because of this, it's carried up into the upper layers of the disk where we don't expect to see it. So that causes the shape here to actually get stretched out and all of the ices to be present at the same location. And it turns out that there are actually laboratory studies, which I won't go into in detail, but it's possible to do exactly what we just proposed to trap carbon monoxide ice inside of either a carbon dioxide ice matrix or a water ice matrix. Um, and we took a look at this in a little more detail with a paper by Jenny Bergner, where we were looking at we have ice in this distribution of the disk. We expect to have more ice located near the midplane, less ice in the upper layers. JWST has this line of sight through the ice in the disk, and we are looking to see if we could model that ice as this layered structure, like we proposed in the beginning with the gumball, or if we need a mixed structure. So if it has a layered structure like this, then you get these profiles for the different features. And you can see that for the CO, it has a very sharp peak. It's very narrow. But if we have a mixed structure where you have a water ice matrix and with a little bit of CO2 and a little bit of CO mixed into it, then you actually end up with a very broad CO feature like this. So it's a very clear signature for when you have layered ices versus mixed ices. And what Jenny found when she modeled this particular source was that actually we have a little bit of a combination of both, but mostly mixed ices. So the CO profile is really wide, and this indicates that you can't fit it with a pure component. So it can't just be layers. You have to have mixed ices in there. And she tried a couple different models. The one that fits the best is this yellow one where you have a mixture of a core layer with water mixed with the other ices, and then another layer of CO2 and CO ice mixed together on the outside. So it looks like what we're seeing is that as these grains were falling in toward the central star, some of the CO and the CO2 ice sublimated. But some of it was still trapped within this water ice matrix. And so that core still has those carbon-rich ices mixed in with it. But there's a layer on the surface where those ices froze back out once they got into the disk, and the disk was cold in the outer part of the disk. So maybe we have this sort of duo structure where the mixed ices are playing a really important role. But Jenny actually took this a little bit further. So she asked, all right, if we have the CO ice mixed in with the water ice, then this suggests that perhaps this gumball actually doesn't look like a gumball. It looks like a chewed gumball. I found this on the internet. It's really disgusting. But you can like what does this do to our picture, our nice neat picture that we had of how you sublimate different types of ices at specific radii and get different carbon over oxygen ratios in different planets. And what does it mean for how much carbon gets into different planets? So she actually modeled this. So she took a series of different layered or mixed ices. So this yellow one here is sort of the classic fit that we talked about. And if you have an entirely mixed ice set, you might not get any snowline features. And if you have an entirely layered or pure ice composition, then you would get this sort of step feature for these different snow lines. So our best fit that she was able to get is this one in the center in purple, where it's a little bit of both. You do have still have some snow lines, but it's just not quite as strong as it was before. And this is how that carbon over oxygen plot would look. So it sort of suggests that actually you might have a little bit more carbon that's making it in closer to the central star. So you could give your terrestrial planets that are forming, closer to the star, you could give them more carbon as they form, and this could mean it could be favorable for life in terms of increasing your bulk carbon abundance that they have access to. So our question of whether terrestrial planets get sufficient carbon and water-rich solids to become habitable, yes, it seems like they are getting certainly as much or more carbon than we thought before, and that is a really interesting result that's coming out of a wide number of JWST programs. So there are a couple things that I think are going to be coming out or that have started to come out are going to be areas that people focus on in the future with JWST in the next few years. So the first is that, I've been talking a lot about carbon in this talk, but actually nitrogen is also very important uh, uh, for life as well, and it's a key ingredient in like a number of amino acids and proteins and things like that. So you can do the same thing that I've just explained here for carbon, but also for nitrogen. So there are complex organic molecules that have nitrogen. So cyanides, for example, and Puna Nazari at ESO has taken a look at this, and she's part of the IPA team and also the JWST team, and they're able to now fit some of these weaker features here, potentially with some cyanides. And there's actually a better slide that I should have included here instead, but there's some new work that's going on with this as well. So that's one thing, and also looking for N2, which is the simplest nitrogen-bearing ice, and we think that's the main ice that carries most of the nitrogen in these disks. However, unfortunately, it has a feature that shows up, or it overlaps with the main CO2 feature, so it's very difficult to disentangle them. So there may be some efforts in the future to try to do that disentanglement and get out how much N2 ice we have. The second thing is that, as I said earlier, the refractory carbon turns out to be really important. So potentially, it's something where if you have 50% of your carbon is in refractory carbon, we don't see that much carbon in Earth. So we would need to come up with some model for how you destroy that carbon, because maybe having that much carbon, there's a question of if it's too much of a good thing for life. If you have more carbon, will you disrupt carbon silicate cycles that make or that are important for bringing up material from the mantle to the surface, and that could also impact the habitability of the planet. So how much refractory carbon we have is something that we really need to start to study. Fortunately, even though we don't see the refractory carbon in absorption in the molecular cloud, we do see these PAHs, the polycyclic aromatic hydrocarbons, in emission toward these protoplanetary disks. So this is a case for my PhD student, Arjun Sturm, where he was able to fit this disk, including PAHs here, as well as ices in these major features. And another one of our team members, Nicole Arwen-Lentham, was able to actually measure resolved PAH emission in a different disk for another JWST program that I'm leading called MIDAS. So she was able to see that really these PAHs are actually associated with the disk itself rather than being something that's in the background region of the molecular cloud. And then finally, one of the next things that will hopefully happen in like a sort of 5 to 10 year basis, while we still have JWST, is that NASA has a call out for potential probe missions, and they're considering an X-ray mission, but they're also considering an infrared mission called PRIMA. And PRIMA gets longer wavelengths of infrared emission than what JWST can do. So if you look at this plot here, the region that PRIMA gets will be indicated in purple. So it actually will overlap a little bit with JWST. So the difference between these is that JWST really targets ices in sort of the upper layers of the disk where they can be seen in absorption, whereas PRIMA would actually get ices that are located near the midplane, which is more directly where you form comets, for example. And in principle, you can observe ices here as well. And there are also bands of complex organic molecules that you could observe there. So we could study more directly the regions of the disk where comets form themselves. All right, so this is the end of what I've prepared. So thank you for your attention, and I'm looking forward to any questions that you might have.